the University of Arizona would like to introduce the Tawaovi microcampus. In January of this year, the University of Arizona solar decathlon teams visited the Hopi Reservation to meet our clients for this project, the Hopi tribe of northern Arizona. They invited us to propose a potential design for a microcampus at Tawaovi, their new off-grid community. While on the reservation, we were able to speak with clients and local community members to gain a better understanding of the vision for this project. Here, we were introduced to many people, such as Andrew, who had been a key advisor for our team on the Hopi perspective throughout this project.
To give context, the Hopi Reservation is located on the Colorado Plateau of the Four Corners region. The reservation is about equidistant to local cities such as Winslow, Flagstaff, and Durango. Our site is on the north of the reservation, away from major population centers in 1st, 2nd, and 3rd Mesa. The reason for this, that our client, the Hopi tribal government, chose to build Tawaovi outside of clan-owned land to protect ancestral boundaries. The blue area on this map is clan-owned. These lands surround historical major population centers that local leaders have maintained for centuries.
On the reservation, centuries of disinvestment and forced displacement of the Hopi people have left the reservation with fewer resources. Many have left to pursue outside higher education opportunities only to struggle to find jobs or homes when they return. This graphic is the population pyramid of the Hopi tribe compared to the entirety of Arizona. As you can see, the Hopi reservation has huge gaps where working-age adults should be. Our goal with this microcampus is to give the Hopi sovereignty over the future of their community by creating educational opportunities at home.
Our site is in climate ASHRAE 5B, which means cold, dry weather for most of the year. Winds from the southwest can reach up to 39 miles per hour throughout the year. Precipitation is scarce. The only rain comes from the partial monsoons in the summer, but sunny weather allows for some of the best solar potential in the country. The climate constraints, client goals, and remote off-grid site informed our design approach. All this came together to design a net positive, FIA-certified, resilient campus fit for all the Hopi people.
The current Tawaovi site is untouched, isolated, and off-grid. The site is only accessible by the main road. The University of Arizona's scope within Tawaovi is shown here. Our project, highlighted in blue, is the largest site and acts as the central hub, connecting the main road to the multifamily and attached housing developments planned east of the campus. We envision Tawaovi becoming a new city and cultural hub for the Hopi people. As the community grows, the 3 University of Arizona projects will become integrated into the larger master plan community.
Within the scope of our site, the campus is broken up into smaller buildings. The focus is on fostering a microcampus for the University of Arizona with an emphasis on agricultural education, culinary school, veterinary school, and metal and wood fabrication workshops.
With 6 main buildings total, the program was requested by the client. In the west, highlighted in blue tones, you can see the campus rec, workshop, and central class spaces. On the east, highlighted in orange tones, there is admin, success center, and the vet office.
The building's basic form began by organizing the program. Our next goal was to preserve the existing site by letting the buildings flow with the natural landscape, while terracing cornfields in the courtyard where the Hopi people can practice their traditional dry farming. The workshop was then bent and screens were raised on the western ends to protect the campus from the prevailing western winds. Finally, solar-shaded parking was added north and south of the campus to supply power to the microgrid. The roof form and clerestories were added to increase the amount of natural daylighting and cultural resemblance.
The materials chosen for the project are commonly found in Hopi vernacular. Natural materials such as mass timber, clay-based plaster, and local sandstone help ground the project within its environment.
We used timber-age prefabricated panels from local Durango, Colorado as our main wall and roof system. These panels use wood damaged by mountain pine beetle infestation that would otherwise be wasted. The wood is used to create COT panels that we're able to ship to Tawaovi, where local workers and students can be taught to create prefabricated panels, developing new skills, lifting the local economy, but also contributing to the recovery of Durango's forests.
These prefab panels are built particularly for this climate. The wall panels have an R value of 53.82, while the roof panels hold a thicker layer of cellulose with an R value of 71.8. Our windows are the FIA certified Alpine Tyrol series windows. It was important for us to achieve FIA certification with the envelope to lower the campus's energy consumption. Using prefabricated panels ensured an airtight envelope with no thermal bridging. One of our client goals, flexibility, was at the core of how we designed interior walls. Our spaces utilize retractable walls in the workshop and classrooms, allowing these rooms to adapt and accommodate a wide range of activities.
Here's an example of such classroom, where the retractable walls have been opened to create a larger lecture space. Various courses can be accommodated in these classrooms, allowing for flexible learning environments and student interactions. We use passive strategies to achieve VS0 certification. In the summer, air quality monitors open operating windows and clear stories to ventilate heat through the stack effect. Overhangs above the clear stories block heat from entering the building. Clear stories let light into the spaces, heating tiles that function as a thermal mass. The wall collects heat and slowly radiates it into the room.
One of the key parts of establishing resiliency within the project was a water conservation system. In such a dry climate, water was essential to the design. Through the terrace farms and our roof drainage system, the campus can collect nearly 150,000 gallons of rainwater annually. In addition, we can retain 109,000 gallons of water for irrigating terrace farming. When monsoon showers occur, rainwater flows from terrace to terrace, bringing the corn crops to life and routing excess water downslope to the water collection tower. The water collection tower then collects and filters gray water and rainwater. The water stored in the collection tower irrigates the terraces and native vegetation on site, while black water is routed to the wastewater treatment facility.
The water then irrigates the terraces, as well as the vegetable garden and greenhouse for the outdoor kitchen. Here, students can learn culinary practices and have access to a wide range of homegrown vegetables. The greenhouse can passively modify humidity levels to grow a wide range of vegetables, while the grow lights illuminate the space in a deep purple. At night, this space becomes a focal point of the terraces. This school is designed with the ability to function efficiently, even outside of school hours. Our electrical and mechanical systems allow for easy zoning of spaces, which work in tandem with passive systems to heat, cool, and light spaces only when they are fully occupied.
Effective air control is necessary in an environment prone to harsh, dusty, prevailing winds. That's why we implemented an ERV system as well as monitoring windows, which work in unison to bring fresh air into spaces while exhausting stale air and removing harmful particles in classroom spaces. This betters health, and fresh air has been shown to improve attentiveness and cognition in students.
Considering our client's goal for cultural continuation, the campus was designed to interact with the community through zones of interest. The campus's programs to provide for community needs, develop the economy, establish cultural amenities, and create recreational areas.
One such community engagement tool is the workshop, where it is a focal point for this project, as it empowers the Hopi through hands-on learning. Participants can build, maintain, and engage in the construction process, fostering skills and confidence needed to shape their own future.
The Hopi people expressed an interest for an architectural language that drew inspiration from their traditional styles of architecture. In developing the mass, it was important to maintain a Hopi identity when designing. We continued this language on the interior, using baffles in the ceiling that help minimize negative acoustics, while echoing traditional Hopi ceilings. In the terraces outside, we created spaces for the Hopi to continue the long-standing tradition of dry farming that has been used for centuries using resilient species of corn.
To make the campus as comfortable and efficient as possible, we utilized daylight models to analyze the lighting conditions in the buildings. Clerestory windows are primarily utilized in the classroom spaces to provide well-lit desktop environments, while areas such as dining and study rooms utilize eye-level windows to provide dimmer spaces with intentional views outwards per Hopi request.
The Success Center is a hub for productivity and social interaction. We tried to balance the culture preference of having dim lighting while still being effective in task, thus creating a welcoming environment for the Hopi. Bright day lighting was also important for the gymnasium. A vibrant center for sports events, it includes a flexible multi-court for sports such as volleyball, tennis, and most notably basketball, a beloved sport among the Hopi.
The clerestories also aided in our energy efficiency, bringing more heat into the spaces in the winter than heat loss, as verified by Woofy. Together with highly insulated prefabricated wall and roof panels, we reached an EUI of -11. We fulfilled the requirements to achieve PHI 0 for new construction. Off-grid means needing excess energy to operate during peak loads in winter months around December and January. Our building's photovoltaics can generate 280,000 kilowatt hours under ideal conditions, offsetting the building's annual consumption even during the most intensive months. This means we can provide nearly 180,000 kilowatts of excess power to the rest of the community annually. This DC power feeds into the Tawaovi community microgrid, contributing to the overall power reserves across all Tawaovi buildings.
Supplementing the passive systems, we use a hydronic radiant system because of its ability to efficiently provide heating and cooling. In our climate where the dew point outside never goes above 60 degrees, which means we don't have to worry about condensation. To maximize efficiency, we split the building into zones for superior occupancy control and comfort. The air-to-water Chiltrix heat pump uses water instead of refrigerant for distribution. Compared to conventional or BRF systems, we have completely eliminated the chance for a refrigerant leak in the building. In spaces like the gymnasium and Success Center, Banco units respond to shifts in occupancy by providing additional heating and cooling. To ventilate, the energy recovery ventilator removes stale air and replaces it with fresh, reconditioned air. It conserves energy and has an 87% heat recovery rate.
In addition to our array photovoltaic systems, we have coordinated with Tawaovi community to work within an islanded DC microgrid using block energy. In addition to our array photovoltaic systems, we have coordinated with Tawaovi community to work within an islanded DC microgrid using block energy, a commercially available product we have partnered with. Excess energy is stored and used to offset loads throughout the community. Since energy demands at the campus peak at different hours than the housing developments, the stored energy can be redistributed where it's needed, keeping the community powered through the day, winter months, and overcast days by sharing excess energy, supporting our community self-sufficiency.
Compared to typical construction, using our low carbon footprint materials acquired locally has allowed the microcampus to reduce embodied carbon significantly. Using one-click LCA, the campus proudly scored a rating of B, despite a remote site.
Thanks to the reduced cost of domestically sourced materials, the campus will cost approximately $282 per square foot, compared to a typical construction cost of $300 per square foot for our site. We estimate that low energy and maintenance costs will save the Hopi people over $5 million over the course of the next 30 years.
In conclusion, with our clients' goals at the forefront, we look to achieve a truly resilient campus through our flexible and adaptive classrooms, water collection systems that reuse rain and gray water, massing and interior considerations that reflect and respect culture, and highly insulated, efficient envelope that achieves BS0. We'd like to thank our advisors and partners who have helped us make this project possible.